This is number 53 in chapter 15. It looks at our Kw equilibrium constant and is basically talking to us from the standpoint that equilibrium constants are temperature dependent. Just like rate constants from chapter 13, which are also temperature dependent, remember the Arrhenius equation, equilibrium constants are also temperature dependent. And so, for instance, our Kw at 25 degrees Celsius was equal to 1 times 10 to the negative 14th, and I presented that to you guys in class. In number 53, the Kw for that autoionization of water is actually equal to 2.4 times 10 to the negative 14th at 37 degrees Celsius. So notice that we have a difference in equilibrium constants. We're talking about the same process, and that process is water ionizing itself to produce hydronium ion and hydroxide anion, right? And so that is our autoionization of water, and that's what Kw is describing for us. And so if we increase the temperature, our Kw increases. And so what they are asking in number 53 is, what is the hydronium ion concentration, and then subsequently what is the pH for this for water at 37 degrees Celsius. So basically we have to look at that autoionization of water. We have to write what that equilibrium constant is actually equal to. So to reiterate, here is our autoionization, here is our equilibrium. And so we have a Kw then equal to hydronium ion concentration times hydroxide concentration. Remember, H2O is a pure liquid, so that is not a part of that equilibrium constant. So we just have to worry about H3O plus and OH minus. Initially, these guys are going to be 0. Because of that 0, they're going to have a positive change. We have to make some of those materials. And so that means at equilibrium, both these concentrations are actually equal as X. And so that means our Kw, which is equal to that 2.4 times 10 to the negative 14th, is going to equal essentially X squared. We take the square root of both sides, and then we get X, which remember is equal to our hydronium ion concentration, is equal to that 1.54 times 10 to the negative 7. So that's our hydronium ion concentration. And now we can solve for the pH. pH is equal to the negative logarithm of the hydronium ion concentration and when we do that math, we get a value of 6.809. So we have a H3O plus concentration equal to 1.54 times 10 to the negative 7th, and we have a pH equal to 6.809. That answers number 53, but I'd like to talk about it just a little bit further with the concept of neutrality, right? And so we've talked about neutral solution, and so we're used to our pH being equal to 7 for something that is neutral. And in this case, we figured that our pH would be 6.8, which for us we would consider acidic. But what we have to realize is that that is still neutral. This is at 25 degrees Celsius, and this is at 37 degrees Celsius. But the fact that our X is equal not only to the hydronium ion concentration, it's also equal to the hydroxide concentration in this case. And so that means we're still talking about something that's neutral. We could actually solve for a POH, and we would get the same thing. We would get the 6.809 because that X value is the same for both of those constituents, the hydronium ion and the hydroxide ion. So this is still considered neutral. But remember again, we are at 37 degrees Celsius, and so that's why we have a change in that neutral point from what we're used to, which is that pH equal to 7. That is number 53.